right, I want to describe Darcy's Law and how we get the permeability, especially for those who did not do the permeability lab before we ended up going on this break. The idea is that we're going to use the equation Q equals V times A that you know from your fluid mechanics class, and remember that A was what? A was the cross-sectional area of the pipe, so we have to keep that in mind when we do these problems. And what Darcy did was that he did this little experiment where we have soil here, and we have water here, and then water at the top here. And the idea was that we would get water to flow upward through the soil. So he maintained a constant head at the top. How was the head maintained at the top? By basically filling this side, we could maintain a constant water level there. And then by having a lip at this side, the water level would remain constant and the water would flow over and we would catch the water there. The soil, we're going to call the length delta L. In other words, the water is going upward through the soil, and in going in this direction, the delta L is the distance that the water travels through the soil. So that is our delta L. And the delta H is the difference between the upper water level and the lower water level. And we are going to define the hydraulic gradient as the delta H over delta L. In plan view, we had a cross-sectional area for the soil. So, in other words, plan view for that soil, the cross-sectional area. And like I say, we maintained a constant head by filling at the upper end, and we measure the flow volume in the beaker and time. So, in a sense, the test is pretty simple. We're just going to measure the volume there over a particular period of time. And for some reason we use small q in soil mechanics. And so the formula that Darcy came up with was Q is equal to KIA. Well, if the velocity V is K times I, then this equation is, it's the same equation there. So the basic equation that Darcy developed is that Q is equal to K times I times the cross-section, where K is the coefficient of permeability of the soil. And the units on small q are cubic feet per second. So when Darcy ran these tests, he chose the delta H, the delta L, and the A, and he measured the Q, and he calculated out what the K was. The soil will influence the K. So, in other words, if you have a gravel, the water travels quickly through the apparatus, and he would get values of K from 10 to the negative second to 1 centimeters per second. Whereas for clay, if you have a clay soil, not much water passes through there, and you get something like 10 to the negative 8, 10 to the negative 7th centimeters per second. For some reason, this is almost always, K is almost always given in centimeters per second. And not English units, or I don't really know why. So let's look at this example. Suppose, so this is called a constant head test. Why constant head? Because we maintain the, in this case, the delta H throughout the test. So for using delta H equals 2 meters, delta L is 4 meters, and if the soil has a K of 10 to the minus 5th meters per second, and a cross-sectional area of 1 square meter, this example is to find I and Q. So by definition, I is delta H over delta L. I is hydraulic gradient. We plug those in, we get hydraulic gradient 0.5. Notice there are no units. It's delta H over delta L, no units. Hydraulic gradient 0.5. And using Q is equal to KIA, we have that the K, the I, cross-sectional area, and we get a Q of 5 times 10 to the minus 6 cubic meters per second. Looking at this test in a little bit more detail, we can draw a flow net for the actual water flow through the soil. And this is a little bit too much detail here, but I'll just walk you through it. So in other words, remember when we draw a flow net, we draw the flow lines. Well, the flow lines are very simple because the water is simply going upward through the soil. So there are flow lines going upward, and then to create our flow net, we simply draw squares going across. And so for this particular example, I can draw this. If you look closely, you can see a flow net. I have 3 flow paths. There's a 1 flow path. There's another flow path. There's another flow path. And I can look at the pore pressures at various points within this apparatus, and we're going to do that. So for this particular setup, it's given that this is 4 meters, this is 1 meter, this is 2 meters. So we have all of our dimensions given, and if I look at that, I'm going to consider different points within the apparatus. I'm going to look at point A, I'm going to look at point B, I'm going to look at point C, and these points are given. I'm using this scale here. If that's 0, that's 1, that's 2.33, that's 3.66, that's 5, because I've broken this up into, I've broken the 4 meters up into 3 equal squares, in a sense. Okay, so let's look at the different points. And yeah, so I've given so in other words, I have my ND is 3. Why? Because I have 1, 2, 3 squares in my flow net, and so ND is 3. The total head drop is 2, so my H is 2. So I have 2 meters over 3 squares. I get 0.667 meters, which is the drop per square. So in other words, I have 0.667 meters per square. That is my head drop. That's my delta H. That's how much the head drops per square. 0.667 meters per square. So I want to determine, using this flow net, I want to determine the, I want to determine the effective stresses at points A, B, and C. So point A is here, point B is here, point C is there. And I'm going to look at it. I'm just going to use the method that we've been doing. So using the scale here, so that's 0, that's 5, 3.66, 2.331. Then I'm looking at point A, it's a depth of 5, B is 3.66, C is 2.33. I look at the figure. So I'm looking at this figure. Let's look at point A here. What do I have? I've got a meter of water, and I have 4 meters of saturated sand. So when I figure out my sigma, a meter of water, 4 meters of saturated sand, my gamma is given as 20 kilonewtons per cubic meter. For point B, I have what? A meter of water and 2.66 meters of saturated sand. So I just look there. Meter of water, 2.66 of saturated sand. For point C, I've got a meter of water and 1.33 meters of saturated sand. So I have a meter of water, 1.33 meters of saturated sand. So I get all my sigmas. How do I get my U's? Well, the U, I'm going to use the flow net to get the U's. That's what we have to do when we have a flow net. Can't get the U just from the water table. Water is moving, it's flowing. So I cannot use my normal, just looking at the water table situation. So what do I have to do? I have to put down a piezometer at each point. Let's look at point B first. So what do I know? I put a piezometer at B, and what do I see? Well, the water level goes not as high as this and not as low as that. It's in between. Why is it in between? Because the water is flowing through here, and that means that the water level in the piezometer will always be someplace between the highest and someplace and the lowest, someplace between the highest and the lowest. So if we look at what the water has gone through the soil from point A to point B, so it's gone 1 square. So I have 1 drop from the top. So what happens? I know that it's 0.667 meters per square. It's gone 1 square to get from A to B, so that the drop is 0.667. So now I have to use the geometry here to figure out what is the water level. So I'm trying to figure out what is that distance there. And that distance will be what? I just look at it. I get, for point B, to get to the top, this total distance here is 5.67. And then I drop down 0.667, so it's going to be 5.667 minus 0.667 times 9.8. I get 49 is my pore pressure. And similarly, let's do point C, because that's the next harder one. For point C, I've gone through 2 squares, 1 square, 2 squares. So my drop will be, my drop will be 2 squares, 2 times 0.667, 1.33 meters. That's going to be the drop. So I just have to figure out for point C, using the geometry, I have to get, so points C there is what? It's this total distance is 4.33, and then I'm dropping 1.33. So this distance here is going to be 4.33 minus 1.33 times 9.8, 29.4. And for point A, well, point A, I don't have to draw a piezometer because this is actually a piezometer right there. So my point A to get the pore pressure is simply that total distance, which is 5 plus 2 is 7. So 7 times 9.8 gives me 68.6. So I get the pore pressure at point A, B, and so I got all those pore pressures, and then I can get a sigma V prime. For each one of these is simply sigma V minus U, and I get my sigma V primes at each point. Okay, so a question, so we now get a pretty good understanding of what's going on in this. And what we want to know is what value of H is needed to get sigma V prime at point A equal to 0. How would I get my sigma, so my sigma V prime at point A right now is 21.2. What would I need to do to get it to 0? Well, what's got to happen? I have to have my sigma V prime as sigma V minus U. So 0 is equal to sigma V minus U. What does that mean? That means that if U is equal to sigma V, then I get sigma V prime is 0. Well, sigma V is 89.8, so if U is 89.8, then I will get sigma V prime equal to 0. Well, what does that mean? I got to figure out the distance to my upper level water table of 89.8 over 9.8. That means that it's got to be 9.16 meters. And that means, so in other words, the distance from point A to the top up here, this has got to be 9.16 meters. If that's got to be 9.16 meters, then that means that the distance from this water level to the, this upper level, that's going to be, that's got to be 4.16. That's got to be 4.16. So that means my H would be 4.16 meters to get that. If H is 4.16 meters, then what? Then I know that sigma V prime at A is equal to 0. All right. So what is I for this situation? And that's what we're sort of making our way to. I is what? Delta H over L. Well, the delta H is 4.16 meters, and the delta L is 4 meters. So in other words, for this whole thing, we know that this is 4 meters, and that means that when my I is 4.16 over 4 meters, we will get a sigma V prime equal to 0. And, okay, this is somewhat of a long explanation, but what do we conclude? That the delta H per square would be what? 4.16 over 3, and my delta L is 4 over 3. In other words, this, looking at each square of our flow net here, that's 4 over 3. So, using our flow net type calculation, we have that our I for all these squares would be 4.16 over 3 divided by 4 over 3 is 1.04. Okay, again, a little bit lengthy explanation, but the end result is that you can look at this is written out a little bit better. There's a little bit of a rule of thumb. So the rule of thumb is this, and it is that for a normal soil, when I say normal soil, if we have a hydraulic gradient approximately equal to 1, then we end up with a situation where sigma v prime equals 0. For a typical soil, and that means what? What is sigma v prime equal to 0? If sigma v prime equals 0, remember the effective stress is basically the contact stress between the soil particles. If the contact stress between the soil particles is 0, that means the particles aren't really touching. And if the particles aren't touching, then what do I know? The soil has liquefied. The particles are floating in the water. The soil has no strength. And so this is somewhat of a rule of thumb. It works pretty well in a lot of different cases. But we end up with that is a way that we can determine whether our soil has liquefied. And yeah. Now, so in other words, upward flow can cause the sand to liquefy. In the lab, we were going to do this experiment. Unfortunately, you haven't been able to see it, but we did this. Or we could do this in the lab, and typically we do this every year. And that is that we create a situation. We have a model that has our upward flow of our sand, and we raise this water level up until we get the flow to come through, and it goes and it basically lifts the sand particles and floats the sand particles such that this sand liquefies, and we create a liquefaction situation, which in practice generally don't want. How can we get natural liquefaction, which is quicksand? You've all heard of quicksand. Very rare to happen in nature. But one way that it could happen is, for instance, if I have, we'll envision like this, a clay or rock down below. I have sand here, and what can happen is it rains. We fill up this sand, and we get a high water table here, and the sand layer is such that water is flowing, and it flows upward here, and what can occur is that if under certain, if we create that hydraulic gradient approximately equal to 1, we can get soil liquefying right there. Now, one other comment that I will make, and actually I don't think, is that it's rare to find this. I'll just say it's rare to find natural quicksand. I'll stop there.